So there's compelling evidence for dark matter, but we don't know what it is. And this could be a workshop on its own, but we'll focus on axions. Axions are one candidate that may make up the dark matter. And as Giovanni spoke about yesterday, they're particularly well motivated because they arise from the Pechi-Quinn solution to the strong CP problem. And they could have many different mass ranges. More strongly coupled, more massive axions would have been easier to find. So if they existed, we should have seen them by now. It leaves us with these lighter, more weakly interacting, invisible axions to try to find. Moreover, from various observatory constraints, we expect them in kind of a micro-EV range. But as Andreas also mentioned, it's actually a lot more open-ended. But this is one of the preferred ranges in micro-EV, which would correspond to a microwave frequency. So how might you detect this incredibly weakly interacting particle? And so in the early 80s, Pierre Sakivi came up with the Sakivi Haloscope, that if we have a very strong magnetic field, so let's apply a magnetic field from, say, a solenoid magnet, but it could be any magnet, the axion can scatter off that field and create a real photon. This would be a very weak, faint signal, but if you had resonant enhancement from, say, a microwave cavity, you can actually ring up that power and have a chance to measure it. But it's still difficult because we don't know the mass of this axion, of this particle, so the resulting frequency is unknown. So if we're using resonant enhancement, we have to be able to shift what frequency we're resonant with. But that can be done. And in the case of ADMX and a number of other experiments at CAP, at Haystack, we use a tuning rod in the cylindrical cavity. So for some tuning rod configuration in the cavity, there's a resonant frequency. We can measure this just doing transmission with two antennas. And then if I perturb that rod, move it a little bit, we've pushed the field solutions around and we've shifted the resonant frequency. So I can scan through listening for different axion mass. And so what would the power of this kind of search look like? It goes with the volume of your cavity. It goes with the magnetic field squared. We have this thing called form factor. That's just the overlap of the cavity mode with your applied B field. That has to do with how much conversion of axions to photons you get. Coupling, which Giovanni also spoke about in more detail yesterday, this is just how strongly the axion couples to photons. There are many models for this. In particular, we usually speak about KSVZ and DFSZ. This power is based off of the KSVZ, which is slightly stronger coupling. However, DFSZ is also well motivated and attractive because it's compatible with the grand unified theory, but it's a weaker coupling, so it would mean less of a signal to detect and a harder experiment. Rho being the density of axions in our local halo, frequency set by the axion mass, and Q being the quality factor of our resonator, how good our resonant enhancement is. To actually make an experiment about this, what would the signal to noise ratio look like? So it goes with the power just described, and inverse to the noise temperature of the system. We can also improve our signal to noise by integrating longer at a given frequency and having a narrower bandwidth. So system temperature is very important, and this comes from both the physical temperature and the temperature of our amplifiers. And there's a bit of an optimization coming from here in that if we integrate for too long, we could not scan frequency space in an effective way. But by having a very low system temperature, a strong magnet, in a sense optimizing our experiment parameters, we can actually scan through frequency space in a realistic rate. So to actually run a haloscope to search for axions, we know that we want a high quality factor resonator, which in our case we use a copper OFHC microwave cavity resonator. We have a strong magnetic field from a superconducting solenoid magnet. We want very low system noise temperature, which we accomplish in two ways, primarily. We use a dilution refrigerator for cooling the experiment, and we have quantum-limited amplifiers. And we'll speak about this more in a little bit. So now, what does this actually look like in real life? This is, again, the insert, in this case, about to be deployed for data taking into the magnet bore. So if we look at this diagram, the blue is our solenoid magnet. The cavity lives inside the bore in the field of the magnet. And hopefully you can see there are tuning rods here for adjusting frequency, antennas to read out power of the cavity. We have a dilution refrigerator that sits about here, so it's directly thermally sunk to both the cavity and our quantum electronics up here. The quantum electronics need to be in a field-free region because they're type 1 superconductors. So we have an additional magnet here that actually cancels fringe fields from the primary solenoid magnet. And then as you move up, you get to the warmer and warmer spaces of the insert. And this is where it actually happens in Seattle. This is at the University of Washington. So the top of our magnet bore is actually right here. In the case of this picture, the insert is hanging from the clean room, being worked on until reinserted and deployed for data. We have a helium liquefaction system where we actually capture warm helium gas in this gas bag, recompress it with these two devices, and liquefy it to be reused as cryogen. And then the data acquisition system and warm electronics live here for controlling the experiment. And one thing to realize and point out is that the magnet actually descends another floor into the ground. Again, this is a solenoid superconducting magnet, 53 centimeter bore, 100 centimeter height. And if we ramp it to full field, it's about 8 Tesla at 230 amps. And so one of the primary upgrades of our experiment in this last and now current run was adding the dilution refrigerator. This is a refrigerator that cools through mixing of helium-3 and helium-4 in a cyclic way. And it actually allows for persistent millikelvin temperature. And we had a custom-made fridge from Janus Research Systems to have a very strong cooling power of 800 microwatts at 100 millikelvin. And this is so the fridge can handle the loads of the huge thermal mass of the cavity, as well as all the electronics up to the top. So still that you can see here drives cyclically mixing helium-3 in this mixing chamber where the cooling occurs and cycles back through. All of this in the middle is just heat exchangers. And so with this dilution refrigerator, we actually are cooling cold enough that there's an advantage to have quantum amplifiers. We do that using both SQUIDs and JPAs, depending on the frequency range. So these are superconducting quantum interference devices and Josephson parametric amplifiers. They have noise temperatures that approach the quantum limit. They're flux to voltage transducers. One thing that's special about our SQUIDs is we actually impedance match using varactor tuning. So this allows us to use the SQUID over a wider frequency range. And these live in the field-free region that we sometimes call the squidadel. And these are both characterized and courtesy of our collaborators at Berkeley, Irfan Siddiqui and Sean O'Kelly. After the initial stage of amplification, the signal moves through to warmer and warmer spaces where we can get away with hemped amplification. We then mix down an FFT, getting a power spectrum out of our cavity. And so actually operating ADMX, there's initially a cool down from room temperature, nitrogen, liquid helium, pumped helium-4, and then finally turning on the dilution refrigerator, mixing helium-3 and helium-4, getting to millikelvin temperatures. If everything's okay, we ramp the magnet, and now we can start taking data, listening for axion to photon conversion. So the cavity is tuned to a particular frequency. We check our coupling and Q factor through S parameter measurements. We optimize, adjust either the squid or JPA, whichever we're using in the given frequency. And then we listen and digitize for about 100 seconds. And after that, we move to the next frequency, looking in a new spot. While this is all happening, there's a live analysis that's constantly checking for a possible candidate, and that would dictate to go back and rescan. One may wonder, how do we actually know that we could hear something? And so, from time to time, a team blind to the rest of us will inject a synthetic axion, and this is actually into the hardware, so it's an actual signal. And then it's checked in the live analysis, did these test signals come through? And this is a case where you can see for many spectra scanning through that a KSBZ signal injected did come up. This being a stronger coupling, higher power signal, you can see it in single spectra. And in the case of our DFSZ signal, after averaging in the grand spectra, it does still turn up. So this is a nice sanity check that we could hear it if it was there. And then, of course, we go back and rescan without the fake injection to actually check the frequencies where this happened.
Sorry, what's the y-axis?
Oh, I'm sorry, thank you. That is just the signal to noise here. And I think in both cases it's the signal to noise.
So why do you have many waveforms?
So we start somewhere and listen. We move a little and listen, but there's an overlap.
So they are
the whole span is order kilohertz, but the stepping is actually closer to 100 hertz. And it's intentional to have that overlap for more averaging. Okay. And so last year, from January to June, we operated with the setup that I just described. And in doing so, we scanned from 645 to 680 megahertz, which would correspond to an axion mass of 2.66 to 2.81 micro EV. At the time, our field was at 6.8 Tesla, and our temperature was 150 millikelvin. And with these parameters, we were sensitive to DFSC axions. And so the results, in the axes here, we have axion mass or frequency, and going down the vertical axis is weaker and weaker coupling. So at a given position, the faintest power signal of an axion to photon conversion we could detect would correspond to a given coupling, and that's drawn here. In the red, it's the case of a Maxwellian distribution line shape. So velocity spread just based on a Maxwell distribution of the axion. The N body is a simulation giving a slightly narrower line shape to the axion. This was done by our collaborator, Eric Lentz. But you will see that in the case of the N body, we completely exclude DFSC axions for this region. And it does waver a little bit in the Maxwellian. And this line here is one sliver of frequency that was removed because of RF interference. Putting this in a broader context, our past work is shown in this light blue. And so what we've done is, for a narrow region, extended the depth that we were able to probe. And this is the first time that an experiment has ruled out DFSC axions. And putting this in a broader context, past results from Haystack at Yale in the higher frequency, work done at Brookhaven and the University of Florida are also shown. However, this also means we didn't find anything, and there's a lot more work to do. But at this very moment, as I speak, we are taking data. So run 1B is in progress. And furthermore, we have a higher magnetic field of 7.6 Tesla. We improved some of the cryogenic infrastructure and are now at 90 millikelvin. And so we'll continue to search now in a slightly higher frequency range of 680 to 800 megahertz. So we may find the axion at any moment, and we will see. In an even longer term, speaking of the future, so the work I just spoke about is in this region. We aim to continue to cover higher and higher frequency space, aiming for DFSC sensitivity. To use a cavity, this means having a smaller radius cavity for a higher frequency. However, then you have a lower volume in your field and less power out. But to get around that, we can use an array of several cavities joined together and compensate for the loss of volume and power. We actually already ran a small cavity preparing the way for this approach. This is Sidecar, and we searched in the 4 to 6 gigahertz and 6 to 7 gigahertz range. This was one of the first piezo-tuned small higher frequency cavities to be used in this way. The results are not yet published, but I can show you the preliminary exclusions done with the small cavity, and this is from Christian Boutin's thesis work, another one of our collaborators. So from listening on the TM010 mode here and here, we excluded this small region, and on a TM020 mode, this slightly higher frequency region. And so moving forward with these small cavities, we have a prototype that's been made, and these are actually piezo-tuned. You can see the rotary piezo device here for moving tuning rods, and linear piezos for adjusting antenna coupling. And so the intention is to use this kind of array to search in the 1 to 2 gigahertz range. And again, this would be combining power from all four in what is still a haloscope search. And as Andres also mentioned quite a bit yesterday, there is reason to look lighter. To make a lower frequency cavity would mean making it wider and wider, which is very hard to get a wider and wider and wider magnetic bore. But you could use that volume differently with an LC circuit, so something that's electrically longer than it is geometrically. So actually adding a capacitor and inductor to get a very low frequency structure. This is the same haloscope principle, just a different resonator. This could be used for, so let's actually look at what that would look like. If I have the same solenoid magnet and apply a magnetic field, the same excitation that drives a cavity has an associated magnetic field oscillating around the axis of the applied magnetic field, and that can be captured with a loop antenna, which has some flux, and just from flux and inductor, there's now a current to read out. I can add a variable capacitor and still have resonant enhancement and tune through, and this could be read out by a squid in principle. So the LC circuit could be used to search in the sub 100 megahertz, sub 100 nano EV mass range. If you assume a Q of 10 to the 4 and millikelvin temperature for the ADMX magnet and the CMS magnet, these are potential exclusions that could be achieved with this kind of device. And this is in context with current and past searches from ADMX. And this dashed line is just the improvement you could get if you had a bigger and bigger magnet in size. So a prototype of this has also been made at the University of Florida. This is actually a superconducting loop strung around a Teflon frame with superconducting plate capacitors, and it's tuned by moving a dielectric in and out of the capacitors, also with the piezo. And we have demonstrated that tuning is possible of this resonant structure in cryo. So this is another possible resonant structure for future Axion searches. And so in summary, Axions are a well-motivated dark matter candidate, especially in light of the strong CP problem. ADMX is the first experiment to attain DFSC sensitivity. We're still taking data, and we'll let you know if we find something. Other resonators are under development to keep extending the range that we can search. I'd like to gratefully acknowledge all of our funders and the collaboration. So, thank you.
Okay, so we have time to have questions. So in the limit from the in the difference between the limit from the Maxwellian and the n-body shape, it looked like it was just an offset. Is there more? Just an offset, or not an offset? These lines were just parallel and nothing else. So, or was there more difference to see? So I mean, I didn't see it so fast. So is there more?
I'm not sure, but I guess looking at it,
structure to be seen?
that's an interesting question, and I'm not sure.
Yeah. Okay. Yeah.
I'll ask Eric.
I was just wondering whether this is.
Just an enhancement in the Q factor?
All you're doing is changing your
you change the line width or something. Huh?
Of the axion.
Of the axion.
Right.
It's frequency independent.
What's that?
It's frequency independent, the change. So that's why.
So therefore there is on this plot there is not much information.
I think that the axion density which is higher, so that your specificity is higher, but then the noise floor of your detector is the same structure. So that's what I'm saying.
Okay. Yeah.
If I'm correct.
That seems reasonable, because all that's happened is that the velocity spread is a little narrower,
Yeah.
so the power is in a narrower bandwidth. That's the only thing changing.
And one thing, I think you should give your LC circuit a name. This experiment, this proposal. When we have this, all these funny names, like it's the same range as an abracadabra, maybe you find some name which is also which we can get. So LC circuit is not very sexy.
Well, if anyone has suggestions, let me know.
So this frequency range that was cut out, it's 1 kilohertz or it's wider? Or?
Oh, I would have to check the paper. I don't remember.
Are you planning to go below the DFSZ threshold, and how much in the future?
In what frequency range?
In sensitivity, for example, in any frequency range, in particular in this, or whether the target is just DFSZ, or you're planning also to run longer to go to lower couplings, or the say if the dark matter is not 100%.
Oh, I think the primary goal is to hit DFSZ.
Yes.
I don't think we'll try to go beyond that, but we should be able to hit DFSC with the array, but we'll see.
And at high frequency, the high frequency setup, will be able to go back down to DFSZ or KSBC? Or?
In the 1 to 2 gigahertz range, we expect so.
Okay.
That would be here.
What's the time? What's the time scale of the experiment to probe this region?
For run 2 or for the current run?
Basically, the region you showed me.
Oh, from the data.
Yes.
That was January to June or July. So
I mean, the time scale of the experiment to probe this region. So to get enough data to exclude this region or to find something there.
how long are we listening at each frequency? It's about 100 seconds.
No, in total for the whole range. I mean, for the whole range we want to probe.
Which range do you mean?
The mass range.
For the single cavity or for
For the forecast.
everything? For the 4 cavities?
Okay.
Everything. Oh, that's years and years. We'll probably be with the single cavity for at least another year, and then years with the array, and then you're only at 2 gigahertz, and so more years for after 2 gigahertz. There's not just the integration time listening, but the turnaround of cooling, which can take weeks, warming up that can take weeks, and all the time of refitting and changing the hardware for each sort of sub-band that you search. And then the R&D for each new resonance structure and the things we learn with each new resonance structure of how to use it well.
So when you move the rod, you have to warm up, or?
Oh, that's actually an interesting point. It moves cold. It actually generates heat though. So if we move too much, we have to wait and cool back down. And that's why the cooling power of Dilution Refrigerator is so important. And that's also why it's nice to go back and rescan sooner than later to save tuning back. There's a huge gear ratio to get a lot of torque moving this rod, so it's very slow to move. But in usual operation, the temperature is stable enough. But if we needed to zoom to a new region or get past a mode crossing, there might need to be some time to cool back down from the heat.
Other questions?
So I have a related question. So yesterday we heard that there are other experiments looking for different mass ranges. So are they as sensitive as, so are the plans to be as sensitive as you are in the same, for instance, to test the DFSZ limit?
There's so many. Which one? I don't know enough specifically of any plan. Of what's published, none have so far.
So essentially ADMX is the most sensitive one. So
In this mass reach, they are
that's what-
best.
Thank you.
And the only.
Okay, so no more questions? Okay, so thank you.